All right, so here's number 12. A radar signal bounces off of an asteroid and returns to Earth. The round trip time takes 1,734.8 seconds. Round to one place past the decimal. So part A says how far away is this asteroid from Earth in kilometers. We're going to round that one place past the decimal. So um, all right. So to do that, of course, we're going to use the fact that the speed of light, which is given the symbol c, is equal to the distance divided by the time. Now, the time that they gave us, this 1,734.4, sorry, 0.8, that time is the round trip time. So the actual time that we want to use in this equation, this time right here is really half of that. So it's going to be 1734.8 seconds divided by 2. Okay, so here let's figure out what that is. Get my calculator. All right, so I've done the calculation. There's the calculator. So it turns out when you divide it by 2, it's 867.4 seconds. All right, so we're going to use that in this equation to figure out what d is. All right, so now to solve this, you basically multiply both. Here, let me just do it. So c is equal to d over t. Remember, we know c, that's the speed of light. That's always the same number. And we now know t. So we're just going to look for d. So we have to manipulate this algebraically. It's not very difficult. Just multiply both sides by t. And then the t's cancel on this side. And so t is equal to, I'm sorry, d. Let's mess that up. D is what I meant to put, is equal to t times c, right? The time times the speed of light. All right, so, and we just found out that the time is 867.4. That is the time it takes the light or the radar signal, which, by the way, radar, microwaves, visible light, infrared, all of that, ultraviolet, X-rays, all travel at the speed of light, c. All right, that's the speed that all electromagnetic radiation travels at. So that value in meters is 3 times 10 to the 8th, but meters per second. So since we want d to be in kilometers, we're going to say we're going to use this number, 3 times 10 to the 5th kilometers per second. And this, of course, is in seconds. The time is in seconds. And so the seconds cancel. The units always have to cancel. So this is going to be the number that's already in my calculator, 867.4. Let's get my calculator. So it's right there. And then I just multiply that times the speed of light, which is 3. Remember, you have to use scientific notation here. Remember, you're never hitting times. You're never hitting 10. And so this calculator, it's the EXP button, times 10 to the 5th. Many calculators, it's an EE button. Sometimes you have to hit Shift EE. All right. Anyhow, so that's multiplying the time times the speed of light. So this is going to be our distance. All right. So the first 2 digits are the only things that are going to be significant to us. So we're going to turn this into scientific notation here. Let me need to do that. All right. So the decimal point is implied back here. So this is 260 million 220,000 kilometers. All right. So the way that we're going to do that is we move the decimal point so that it's one place past the first digit, right? Just normal scientific notation. So it's going to be 2.6, and then if I move the decimal point, it goes 3 places, another 3 places, and then 2 more places. So that's going to be 8 places. So it's 2.6. 2.6. That's a decimal point right there. times 10 to the 8th kilometers. All right, so that's the distance. All right, that's what we're looking for. And this is part A. All right, so that's part A. All right, so part B is they give us the angular size of the asteroid in arc seconds. All right, so we're gonna I'm gonna do that example in just a moment. Um, once you know the distance, right? So I already have it up here. The distance is 2.6 times 10 to the 8th kilometers. The actual size of the asteroid, and this will be the diameter of the asteroid. All right, they'll give us it'll give us in this the same units as the distance. If the distance was in miles, then the size of the object would be in miles. Normally we use kilometers, so this is also going to be in kilometers. All right, let me get some room and we'll redo this problem, or we'll do part B. All right. To do part B, let's look at the equation sheet for just a moment. Notice there's speed is equal to distance divided by time. Of course, that's the part that we use for part A, where the speed was the speed of light, so it gets its own special symbol, c, which I think I have down here. Anyhow, all right. But anyhow, yeah. So c is there's c right there. So c is 3 times 10 to the 8th meters per second, or if you were in kilometers per second, all right, it's 3 times 10 to the 5th kilometers per second. All right. So that's how you got part A, and the whole purpose of that was to get d, the distance. So the way that this works, this is the equation. All right. That we're going to use. What does this equation describe? This is actually, remember, that's what equations do, is they describe nature, right? That's the whole purpose of them, that we use these in science. It's not because we just that we happen to like math a lot. We like it in particular in astronomy and chemistry and physics. We like it because it describes nature. Right. So what this does is, if let's say you take some object like a chair, right? I usually do this example in the classroom. All right. So just you can imagine in your head you're looking at a chair. Now, if somebody were to move the chair away from you, the chair does not physically change size. We all know that, all right? But as something gets further and further away from you, it looks smaller and smaller, right? So that what that is that's the angular size. That's what alpha is right here. So the L this script L here is the actual size of the object, all right? So the actual size is well the angular size gets smaller and smaller with greater distance, right? If you put the d on the other side of the equation, you can see how that's related. Now the actual size of it, L, the script L here, doesn't change. So since we know what alpha is, they gave us that in the problem, and now we know what D is, that's what part A is all about, we can use this formula as long as alpha is in degrees, all right? So that's the main thing. You got to switch alpha to degrees, all right? And then we're going to figure out what script L is. All right, so this is the equation that we're going to use to solve part B. And what we have to do is we have to change this angle, right? So they give us the angle as point. This is a very small angle, by the way, 0.228 arc seconds. So this is what alpha is, all right? So they start out with alpha is 0.228. And I'm just going to use 2 hash marks. It's just easier than writing arc seconds. So I've got the conversions over here. We have that 1 degree, and you can write it degree, or you can write it with a little circle, is equal to 60 arc minutes. And so a single hash mark means arc minutes, or you can write the word arc minutes. And 1 arc minute is the equivalent of 60 arc seconds. So it's like you take a degree, you break it into 60 equal parts. This is angles, right? So this, like, imagine like taking a degree and you slice it into 60 equal slices of pie, little pieces of pie. Um, right, not pie, the number, like an actual piece of pie. Um, so that's a very very small angle in the sky, and then of course with telescopes you can go even further than that. Then you go into what are called arc seconds. So you take one of those arc minutes and that divide it into 60 um, equal chunks, and one of those is called an arc second. All right, all right, so what we have to do is we have to convert between um, degrees, arc seconds, and degrees. All right, so here we go. All right, so it turns out that there are 60 arc seconds in 1 arc minute, and it turns out that there are 60 arc minutes in 1 degree. I'll write degree like that. All right. So it's a single hash mark, um, and now see, notice like the two hash marks cancel, the one hash mark cancels, and so you just take this number and notice how small this is going to be. 0.228 divided by 60 and divided by 60 again. That's going to be the number of degrees. All right. So let's get our calculator. Let's see. Here's our calculator. And of course, this is well, I can just type that back in. All right, so it's going to be 0.228. All right, and then what you do is you divide by 60, and you're dividing by 60 again, right? Because it's divided by 60, divided by 60. Or you could just say divided by 60 squared. All right, and so this is an extremely small number, right? Look at that. Right, 6.3. If you just round it right there, 6.3 times 10 to the minus fifth. Notice the little e with the minus fifth. So that's a really really small number, right? So I'm going to write that down. 6.3 times 10 to the minus fifth. That's the angle, and then, of course this is in degrees. All right, so now we're ready. Now we can plug everything in. Right, so here we go. Script L is equal to, well, it's just pi over 180. That's just a number, right? That never ever changes. And then times our distance, which was approximately 2.6, that's 6 times 10 to the eighth kilometers. All right. So the fact that that's kilometers is going to make our script L, the actual size of it, also in kilometers. All right, and then we multiply this times 6.3 times 10 to the minus fifth, right? Degrees. That's got to be in degrees. That's a little degree symbol. All right, so we're almost done. And so notice I've already got the answer right here. It should turn out to be 278.6 kilometers. All right, let's actually see that for ourselves. All right, so there's the angle. It's already in here. So I'm just going to multiply that times the distance. All right, so it's going to be times 2.6 times 10 to the eighth. All right, and then times pi, and then divided by 180. All right, so that's exactly what we get. So if we round it to one place past the decimal, so this is 287 point. That's close enough. 287.4 using Mike. I think when I originally did this, I didn't. I used the unrounded version of the distance. Okay, so it'll be slightly different, but that's close enough, right? That is more than close enough. All right, right? So, and there's the answer, right? 278.4